We always think of quantum particles as being just fundamentally unpredictable. But what if there was a way to make them behave just like the everyday objects we see around us? Well, a brand new method might have just cracked the code on how to tame their chaotic dance. So, let's get right to the heart of it. What's the big mystery here? Why is it so ridiculously hard to predict where a quantum particle is going to go? I mean, sure, we can pinpoint its location right now, but figuring out where it'll be even a split second later, that's always been a super fuzzy business. So, what's going on? Well, the answer comes from one of the absolute weirdest truths about our reality. Tiny objects, like an electron, aren't just little points. Nope. They're also waves, described by something we call a wave packet. And here's the problem. These wave packets, by their very nature, just love to spread out over time. They turn a single precise location into this big blurry cloud of possibilities. And this brings us right to the core of the challenge. This spreading out, this quantum wobble, let's call it. It's all dictated by one of the most legendary and powerful equations in all of physics. Yep, I'm talking about the Schrödinger equation. You should think of it as the official rulebook for the quantum world. It tells you, with perfect precision, how a particle's wave changes from one moment to the next. The problem isn't the rulebook itself, it's that the rules are just mind-bendingly complex to follow. Trying to actually use the Schrödinger equation to track a particle, especially when it's getting knocked around by outside forces, is just a beast of a task. The math gets out of control fast. It really is like trying to predict the exact path of one single ripple in the middle of a hurricane. But what if there was a smarter way to read that rulebook? And that right there leads us to the big idea in this new research. It's this incredibly slick method that makes the problem way simpler by basically splitting the action into two totally different jobs. Now, to get this, we have to meet the engine of the Schrödinger equation. It's called the Hamiltonian, and we label it with a capital H. The Hamiltonian packs in all the information about the energy and forces in a system, and it's what really determines how everything changes over time. It's the part of the rulebook that actually makes stuff happen. So here's the breakthrough. Instead of trying to wrestle with the whole complicated Hamiltonian at once, this new method says, hey, let's just break it down. Let's decompose it into two way simpler, way more manageable pieces. Okay, so this method splits the rulebook into two jobs. Let's think of it like a car. The first part, this HP, that's like the car's blueprint. It tells you the car's shape, its color, its design, but it doesn't make it move. The second part, HC, that's the engine. That's the part that actually provides the power to make the car go. And this is the absolute genius of it. By separating the blueprint from the engine, you can focus only on the motion itself. Suddenly, the problem of predicting where the particle is going becomes so much easier because you're not getting bogged down with all the other details that describe what the particle is. Okay, that's a really cool idea on paper, but, does it actually work in the real world? To figure that out, the researchers had to put it to the test on a total classic of a quantum mechanics problem. They chose the perfect test case, the driven harmonic oscillator. Trust me, this thing is a cornerstone of physics. And if their method could handle this, it would be a massive proof that they were onto something huge. So what in the world is a driven harmonic oscillator? Let's just use an analogy. A harmonic oscillator is basically just a ball on a spring, bobbing up and down. Driven just means we're adding an outside force. We're literally pushing that ball back and forth. And in our quantum world, the ball we're trying to track is our particle's wave packet. All right, so the stage is set. The researchers applied their powerful new method to this quantum ball on a spring. The big question is, what did they find? What did this new way of looking at the problem actually show them? And the result was, well, it was just stunning. It was something that nobody had really seen before in this kind of system. It was a genuine, wait, what? Moment that kind of challenges everything we think we know about how quantum particles are supposed to act. Don't just take my word for it. The researchers themselves put it perfectly. They said what they found behaves just like a classical particle whose motion obeys the classical dynamics. A quantum particle acting classical? I mean, come on, that is a huge deal. What they had discovered is something called a non-spreading wave packet, or NSWP for short. This isn't your normal quantum state. It's a very special kind of wave that can move through space, but totally resist that natural urge to spread out. It just holds its shape, staying nice and compact and, well, predictable. Just let that sink in for a second. All that quantum fuzziness we talked about at the beginning? Gone. It just vanished. The wave packet didn't spread out at all. It just glided through the system, holding its shape perfectly, and its path was the exact same one you'd predict for a normal classical object, like an actual ball on a real spring. It's wild. Now, a claim like that is pretty extraordinary, right? So it needs some extraordinary evidence to back it up. And the researchers delivered with some incredibly detailed computer simulations. So let's look at the actual data. Let's see the proof. Okay, check out these two graphs. The red line, that's the path a normal classical particle would take. The little blue dots, that's the calculated position of the quantum wave packet's peak. And just look at it. It doesn't matter if the force is non-resonant, like on the left, or resonant, on the right. The agreement is absolutely perfect. The quantum particle is following the classical path to a T. But this next graph, this is the real kicker. This shows the uncertainty, the fuzziness of the wave packet over time. If that wave were spreading out, this line would be shooting straight up. But look at it. It's perfectly flat. This is the smoking gun. Its shape is completely locked in. It is not spreading out. Period. And what's amazing is that this holds up even when they push the system really hard with a lot of energy. That little wave packet gets thrown all over the place, but it stays as this perfect, non-spreading shape. It's an incredibly solid and, honestly, beautiful result. All right, so let's just quickly recap the big takeaways. Number one, there's a new method that makes quantum motion way easier to understand by splitting the rulebook, the Hamiltonian, into two separate jobs. Number two, this method uncovered these things called non-spreading wave packets in a system where we didn't know they could exist. And finally, number three, and this is the most mind-blowing part, it shows that under the right conditions, a quantum particle can totally ditch its weird fuzziness and act just like a predictable classical object. You know, this work really peels back a layer of what we thought was just unavoidable quantum weirdness, and it shows this surprising, elegant simplicity hiding underneath. And it really forces us to ask a pretty profound question. If a quantum particle can act classically, what else have we been missing this whole time?